Hi, I'm Dr. Matthew Michael. I'm a lecturer here at NGIT. I teach mathematics, and, well, mostly what I'm talking about in these videos right now is differential equations, specifically those out of the 10th edition of Boyce and Prima, as you see on your screen right there. I grabbed their PowerPoint slides so that you can see what I'm thinking of as a mathematician when I'm reading through the material, talking about it. So, we've talked about two of the key cases for these homogeneous equations of this type, and that the quadratic formula of the characteristic equation which solves these or finds their fundamental forms is what you see there right there in the middle. However, we've talked about when b squared is bigger than 4ac, which is the real and repeated case, real and distinct case. But, and we've talked about when b squared is smaller than, when we get complex and imaginary roots. This case we're going to call the repeated roots case. This is the case where b squared is exactly equal to 4ac, because in this case the discriminant is equal to 0, and both roots have the value of negative b over 2a. That's a problem because you can't take the Wronskian with only one equation, one function. Doesn't make sense. So what we're going to have to do is think a little outside the box to try to determine another function that might work. Well, it helps that we know that y1 is already a solution. So what about if instead of y2, or they call it y2, I like to call it y, let's say that, normally when we find a full solution, we call it C1, Y1. And so notice we say Y2 is equal to something times Y1. We're going to say that that itself is a solution. Well, I mean, obviously, a constant times Y1 would be a solution. But we want to make Y1 and Y2 linearly independent. We want to make sure that the Wronskian is not 0. So if y1 follows that exponential form, let's say y2 is that exponential form times some undetermined equation, some v of t. And we're going to solve for v of t in this particular form in order to determine what it might have as a solution. So if y2 is a solution, that means we can plug it back into the differential equation. So notice what we do down below. We take the derivatives, the first and second derivatives of the function itself. And then we plug it back into the differential equation. Yes, that's a lot of math, okay? A lot of algebra. First step, notice there's an exponential that we can move out. Exponentials never equal to 0, so they don't really matter for what we're looking for. We want to find v of t, so get rid of it. After we expand the form, after we expand everything out, note that things start canceling out. That as long as we're careful, things start canceling out. Notice the v prime terms cancel out. This v of t term, when I go and I look for common denominators, well, since we know that this is a repeated root, I know that 4ac is exactly equal to b squared. So that term cancels out as well. So all we're left with is a v double prime is equal to 0, or v prime double prime is equal to 0. Integrate twice. It turns out that your v of t term is a linear function. Remember, this isn't what we're looking for in and of itself. We're looking for another form of that. And so once I plug that into y2, because remember y2 is going to be your original function, the exponential, times v of t. Well, when we plug that in for v of t, it turns out that the repeated root is the same as y1, but times t, times your independent variable. So repeated roots, if I have one extra root, if I have one repeated root extra, that means I do the exact same as the y1, but now multiplied by my independent variable t. If I had a third order system that was repeated in roots, I would add a t squared. If I had a fourth order repeated roots, I'd have a t cubed, and so on and so forth. Now, remember this has to pass the Wronskian test, right? The Wronskian determinant. So take the Wronskian of these two, and it turns out we get an exponential. And as we determined from section 3.1, this works. We're good with that. So this repeated roots formula does indeed fund the fundamental set of solutions. So let's play with it. So this is a repeated roots problem. Easily factorable because it is a perfect square. R plus 2 quantity squared is equal to 0. So plug that in to the form. If you did it via that reduction of order formula, or if you use something else, you'll notice we do indeed get the roots that we want. Right? Notice v of t is once again the linear function. So that means my solution form for this is going to be y1, which is e to the negative 2t, and y2, which is t e to the negative 2t. If we notice that in both of these cases, we're going to get solutions that are going to go to 0. Because if you use L'Hopital's rule, both terms have dominating exponential functions which have a negative root. And it's going to decay regardless of what C1 and C2 might be. Here's an example that you see there. Initial position of 1, initial slope of 3. Here's another case where my repeated roots is once again a perfect square. This time r is equal to 1/2. Now that means that it's going to have a positive root, which means it's going to grow in size. Either grow positively up to infinity or go down negatively to negative infinity. When I plug in my initial conditions, that means I have an initial position of 2, an initial slope of 1/3, so that's almost flat, but just a little bit of positive. What we need to do is we solve for the two terms, C1 being 2, C2 being negative 2/3. Now this one's a little bit tricky to figure out who's going, where is it going? Is it going to positive or negative infinity? So what we do is we consider the two forms between y1 and y2. I mean, obviously we could plug it into the graph, but if I wanted to sketch this without plugging this into Mathematica or Maple or MATLAB or Wolfram Alpha, I need to consider the two different functions. They both share an e to the t over 2. So both of them are equal in that respect. The other one is, the other term that we need to consider is for the first one we have a 2 out front, and for the other one we have a negative 2/3 t. So we need to think which one dominates. Which one will be more massive? A constant 2 or a linear 2/3 t? Because 2/3 t will eventually dominate the constant 2, which is always 2. That means it must be going in the negative direction. But notice, if I move my slope from a positive 1/3 to a positive 2, now both terms are positive, which definitely is going to grow up to positive infinity. So in other words, we can actually solve for it. We can actually find that there might be some critical value or some critical slope value which causes my graph to go from an exponentially growing function in the negative direction to an exponentially growing function in the positive direction. I already referred to this briefly before, but the method that we use to solve this can actually be generalized to what's known as a reduction of order form. So whenever we set y2 to be some function times y1, what we're doing is reducing the order of the problem. Notice last time it was possible we brought down the function's difficulty level considerably. And this is simply from plugging this formula in. y2 is equal to v times y1. And this can be really useful in a case where you might know what one of the solutions is, but not what the other one is. Because frequently you can find one R value that might work for the equation, but you might not be able to determine the other one easily. So this reduction of order formula can really simplify your life. So if I plug that definition in and I find y1, if I find y prime and y double prime and I plug it back into the ODE, I can start collecting terms to see what might happen. So plugging that in, notice that the differential equation itself, y1, already is going to simplify down to a 0. That's why you won't notice any y1 double primes there, because v times y1 double prime, which goes from here, v y1 prime and v y1, well, they all, notice right there, this right here is equal to 0 because it is the differential equation itself. And we already know that y1 satisfies the differential equation. So that term is equal to 0. So, in other words, that v term, anytime when just v shows up, that doesn't matter. Well, it does matter. That term ends up being canceling out. And so it reduces down to a problem for v double prime and v prime. But both of those are derivatives in itself. And so what I can do here is I can start renaming things to make my life easier. So let's take a look at this problem here so we can more easily see what I'm talking about. You can see it at the very bottom. But notice in this case, I know I'm given that the solution y1 is equal to t to the negative 1. If I do reduction of order formula and plug it in, I'm going to be able to reduce the problem down to, that's the second to last line here, 2t v double prime minus v prime is equal to 0. Now, I don't want to solve a second order differential equation. I'm already trying to solve one anyway. So what I do is I say, look, the lowest order derivative is v prime. There's no v. So why don't we call a new function u equal to the derivative of v? Well, that would mean that v double prime, or the derivative of v prime, could be considered u prime. In first order systems, I can solve easy peasy. So now I have a system of equations that I'm going to have to pay attention to, but moving the u to the other side, dividing by u and dividing by 2t, I'm going to end up getting the natural log of u plus 1/2 natural log of t plus c. In other words, if I move the 1/2 up, notice here, this plus c term here means that I have a constant that u is equal to c times t to the 1/2 power, or c square root of t. Remembering that u is v prime, plug v prime back in. And now I can solve for v, because once again I'm just doing a simple integration. The integral of ct to the 1/2 power is 2/3 c t to the 3/2 power, plus a new constant k. So plug that in to the form of y2, right? Because v is not what I'm looking for. V is my stepping stone to my new function y2. So since y2 is v times t inverse, expand that out. I get y2 is equal to 2/3 c times the square root of t plus k t inverse. But I don't care about t inverse because that's already taken care of. So this means that my y2 is just that first term. Let k equal to 0, let c equal to 3/2. We can see that y2 is equal to the square root of t, which should look very familiar. We've already seen this in an earlier selection of slides. And in those slides, we calculated the Wronskian was 3/2 times t to the negative 3/2 power. So this is a way that we can determine that, yes, the solution form that I got last time was indeed correct. Hope this helps.